All right, so this is going to be chapter 19. Go ahead and open up the PowerPoint. Okay, so this chapter for physics 102 is going to be talking about the electric potential and the energy and electrical potential. So what is the potential difference? Potential difference, or what we call voltage, is the electric potential energy per coulomb of charge. Potential difference thought of as the work of unit charge can perform as the charge travels from one point to another. Now, your voltage, your potential difference, is going to equal to your work done divided by your charge transferred. Now, the unit for the volt is going to be volt, and the unit for volt is going to be volt, which is going to be this is going to be joules for your work, and coulomb for your charge, so it'll be your joule per coulomb. So the volt was actually named after Alessandro Giuseppe Antonio Anastasio Volta, which he died in 1827. There's a unit potential difference, and it's equal to 1 joule per coulomb. So let's go ahead. Let me actually go ahead over here. So this is going to be Physics 102, Chapter 19. So we said we defined the potential difference as your work over your charge. So this is going to be your work done. This is going to be your charge. And this is going to be your potential difference. Now, supposedly if you have a basketball and you're dribbling that basketball down. So let me actually get a different color. Let me just get orange for a basketball. So let's say you have a basketball. And your basketball, and you actually is going up and down. So here's your basketball right over here. And this is your ground right over here. So let's say this is A, this is at place B. Now, your height from over here, that's going to be a height for your basketball A, which is from over here, that's going to be your height for basketball B. Now, your weight, your force is going to be your weight, which is going to be your mass times your gravity for each one. So you get your weight over here, which is your mass times your gravity. That means your work done from A to B is going to equal to your gravitational potential energy, which is going to be your mass times gravity multiplied by your height for ball A minus your mass times gravity multiplied by your height for ball B, which is, that one is going to be your gravitational potential energy. We saw that before. And this one is going to be gravitational potential energy. So this is going to equal to your gravitational potential energy for ball A minus gravitational potential energy for ball B. And again, let me actually go ahead and write this down in case you forgot it. Your potential energy, that's going to be your mgh, and your mg, that's your gravitational force. So your work is going to equal to your gravitational force multiplied by your height. Well, the same thing is true for a charge. So supposedly we have a charge. Let me just actually put this over here. Let's say this is your negatives, and this is your positive charge. and you get a charge, I'm going to call it Q naught, for instance, or Q, charge Q. And this charge be coming right over here. So this is actually, let's say, place A, place B. So your weight or the force that's going on it, which is going to be your weight for that one is going to be your Q naught or Q, you call Q. So your charge multiplied by the electric field. Same thing for this one. Your F is going to equal to your charge multiplied by the electric field. So which means that we said our potential difference was your charge over, your work over your charge. That means this is actually going to be your work that's going on from A to B over Q, not over Q, over that test charge Q that we have, is going to equal to the electric potential energy for A divided by that charge minus the electric potential energy for part B divided by that charge. Now again, your work, that's your force multiplied by your distance, your definition of work. So when we're actually talking about the electric potential charge, that's going to equal to your force multiplied by your radius, which is your distance. So maybe I should get this color. So your work from A to B over Q, which is your voltage, is going to equal to your electric potential energy divided by your charge. Which means that your electric potential energy actually is going to equal to your voltage multiplied by that charge. So the difference in the voltage, the potential difference is going to equal to your voltage from B minus your voltage from A, which means for electric potential energy from B over the charge minus electric potential energy for A over that charge, which is going to equal to minus W, your work from A to B over that charge. So your potential difference is going to equal your work minus A to B, minus your work from A to B divided by Q. Now, let me actually put this on a side note, that the electric field is going to equal to your voltage over your distance. That means also your voltage is your electric field multiplied by your distance. Now, taking this one, let me get a different color. That means your potential energy, your potential energy is going to equal to your Q delta V, which is going to be that charge multiplied by your V final, which is your V for your B minus your V initial, which is your V for A. And that's exactly what we just saw. So we talked about having the gravitational potential energy and how we compared it to the electric potential energy, which is your work from A to B equals your electric potential energy from A to B. And we went ahead and we defined the electric potential energy. We just did this equation. So let's say we have a question. The work done by electric force test charge is 2 times 10 negative 6 moved from A to B is 5 times 10 negative 5 joules. Find the electric difference between these 2 points and determine the potential difference between these 2 points. So this is example 1. All right. So we got our charge, which is 2 times 10 negative 6 Coulomb. And our work is not minus 5, it's 5. 5 times 10 negative 5 joules. For part A, we want to find the difference in electrical potential energy. So your difference, your work from A to B is going to equal to your electric potential energy from A minus your electric potential energy for B. Now, the electric potential energy for B minus the electric potential energy for A, that's going to equal to, if you actually move this, again, equal to you minus from A to B, which is going to be minus 5 times the negative 5 joules. So just the negative of this one. For part B, let's see what part B asks for. Determine potential difference. So we're looking for the voltage. So your delta V potential difference is going to be VA minus your VB. Your voltage your voltage at B minus your voltage at A, which is going to equal to your minus work from A to B divided by that charge. So it'll be minus 5 times 10 negative 5 divided by 2 times 10 negative 6. And we should get 5 divided by 2 is 2.5. And then you got negative 5 plus 1. So, and you get the negative over here. So 25 times 10 to the 1. So 2.5 times 10 to the 1. So equals to 225 volts. Perfect. Now, so when we're talking about an energy for that an object can have, we're talking about the total energy. So your total energy is going to equal to your 1/2 mv squared, which is going to be your kinetic energy, plus your 1/2 I omega squared, which is going to be your rotational energy, plus your gravitational potential energy, plus if you have a spring, it'd be 1/2 kx squared. Now we're going to add to it also your electric potential energy. So this is going to be your electric. So if an object, if we include electric potential energy as a part of total energy that an object can have, so your energy is going to equal 1/2 mv squared plus your 1/2 your kinetic plus your rotation, which is 1/2 I omega squared, plus your gravitation, which is mgh, plus your spring, which is 1/2 kx squared, plus your electric potential energy. All right, so let's go ahead and do this example. A particle has a mass of 1.8 times 10 - 5, and the charge is released from a point A, accelerated horizontal until it reaches point P. The only force acting on the particle is electric force, and the electric potential at A, the voltage is 25 volts greater than at B. What is the speed of the particle? And if the same particle has negative charge and were released from a point B, what would it be at A? So let's go ahead. I think this is called example 4. So over here, let me just look at the numbers one more time. 1.8 and 3. So your mass is 1.8 times 10 - 5 kilograms. And your charge is 3 times 10 - 5 coulombs. and your potential difference is 25 volts. Now, the energy at B is going to have to equal to the energy at A. And so for part A, we're looking for the speed at B, and we'll do part B in just a second. So let's do part A. So we said the energy is going to equal both each other. So basically, and let me just write this down, EB equals EA. That means, now looking at it, what do we have? We have a kinetic. We do not have any rotationals or gravitational or spring, but we do have electric. So we're going to have, let me go ahead and write this down. 1/2 mv b squared plus the electric potential energy for B is going to equal to 1/2 mva squared plus the electric potential energy for A. Now, solving this for VB, let me actually go put this by itself. The velocity at B is going to equal to 1/2 mva squared plus the electric potential energy at A minus the electric potential energy at B. So solving this, you get 1/2 mbb squared equals 1/2 mva squared plus, now the electric potential energy, let me just write this down as blue. We said is going to equal to your velocity, your charge multiplied by the velocity. So in this case, what we're going to have, we're going to have the charge multiplied by your velocity A minus your velocity at B. Solving all this, so VB is going to equal to your square root of go ahead and cancel the m, so your m's cancel over here, so you're gonna have to divide 1 by m over here. So it'd be, and you get the 2 is coming up there, so it'd be 2 q naught. Now actually, let me get the black. These two is going to actually be your potential difference. So to be TQ multiplied by your delta V divided by your M. So this is going to equal to square root of 2 times 3 times 10 negative 5 multiplied by 25 divided by your mass, which is 1.8 times 10 negative 5. Now let's plug this in. All right, I got 9.1 meters per second for part A. For part B, right now we want to find the velocity at A, which if we actually do this, we should get -2. If we do the same calculations, we should get -2 Q naught, or Q, the charge, multiplied by delta V divided by M, which is going to equal to -2 multiplied by 3 times 10 negative 5 multiplied by 25. Actually, it'd be -3. It'd be minus 3 because we're not, yeah. So it's not divided by your mass, which is 1.8 times 10 negative 5. So you still get 9.1 meters per second. Now, the reason we put a negative because it said in the question the same particle had a negative charge. So actually that's why we had a negative on this one. I just noticed that when I read the question. Awesome. Now, let's see. Now, so we said that the voltage or potential difference is going to equal to your work over your charge, which your work is your force times distance over your charge. Now, the force, the electric force, okay, let me actually write this down. So this is going to be the electric force, which is going to be K, Q1, Q2 over R squared. Your distance in the charge is going to be the radiuses. So plugging this in, what you're going to have? You're going to have your electric constant, K, Q1, Q over R squared multiplied by R multiplied by that one charge Q. Well, looking at this, our R's cancel out and our Q's cancel out. So your voltage is going to equal to your electric constant, which is 8 times 10 to the 9th power, multiplied by the charge, divided by R. So, and this is actually what we just did. We defined the potential for point charge as your electric constant multiplied by Q divided by R. Actually, let me just write this down over here. That's the electric constant. So K is your electric constant. Now your electric constant, let me go ahead and write down the value for it. It's 8.99 times 10 to the 9th power Newton meter square per Coulomb square. V over D. Yes. All right. And if I press the cardinal law, I'll go. So your F equals KQ1Q over your charge over R squared divided by that charge. The charges cancel out. So what you're gonna have KQ over, I forget to put the square, over R squared. Now, this basically is KQ over R multiplied by R. KQ over R, that's your voltage. So this is going to equal to your V over R. So your delta E for electric field is going to equal to minus dV over the distance D. Again, V is the voltage and D is your distance. Now, your charge which is going to be your something called your capacitance multiplied your capacitance multiplied by your voltage. So C is your capacitance. This is your voltage. And this is your charge. That means well, before we go through that, I need to introduce a different, hold up. So your charge equals capacitance multiplied by the voltage. Now, before we go, I'm going to introduce something called K. K, or kappa, that's your dielectric constant. Now, by putting the dielectric constant between the plates of a capacitor, let's say you have a capacitor that has two plates, right? So you got plate A, plate B, and the capacitor does the whole charge. So the capacitance can actually increase with a better dielectric constant. Now your dielectric is going to equal to your E naught over E. That means that the electric field is going to equal to your E naught divided by your kappa, your dielectric constant. Now, what is E naught? Now, your E naught, initial electric field, is going to be Q over epsilon naught multiplied by A. A, that's your area. Q, that's your charge. And epsilon naught is your permittivity constant that we talked about before. And this, again, I'm going to put down the value, 8.85 times 10 negative 12 coulomb square per Newton meter square. Now, if you substitute this in there, what you're going to have for the electric field, that means your electric field is going to equal to Q over epsilon naught A multiplied by your kappa, which is going to equal your velocity, your voltage divided by your distance. That means if you actually solve it for your charge, what you're going to have? You're going to have your dielectric constant multiplied by the area, multiplied by your epsilon naught, multiplied by your voltage, divide all that by your distance, if you actually solve it for these two. Now, your kappa multiplied by your dielectric constant multiplied by the area multiplied by the permittivity divided by your distance, we give that C, and that's actually your capacitance. And that's where you actually, again, where we started off, where we said the charge is going to equal your capacitance multiplied by your voltage. So that's where you get your charge is going to equal your capacitance multiplied by your voltage. Now, I need to mention that the energy equals 1/2 CV squared, which is going to equal to 1/2, again, for your capacitance, as your dielectric constant multiplied by your permittivity, multiplied by the area divided by your distance. And for V is going to equal to your electric field multiplied by your distance. And this is going to be square. Now, we defined the voltage earlier. Now, your energy is going to equal 1/2 CV squared, which is 1/2 kappa epsilon I, your area divided by distance, multiplied by ED squared. So let's actually go ahead and break it up. Kappa, your dielectric constant, E naught A E squared D squared over D, 2D actually. So one of these cancel out. So what you're going to have, now if you actually, let me actually write this down. K epsilon naught A E squared D over 2. Now, your distance with your area, that's going to be your volume. So your energy density which is going to be your energy over your volume, and it's going to equal to 1/2 dielectric constant permittivity multiplied by electric field squared. And this is what we just did. We looked at the equipotential surface, the surface on which electric potential is the same everywhere, and we defined that the voltage equals KQ over R. And again, K, that's your electric constant. So there's a question over here. Go ahead and pause this video and work on this question, and you should get the answer at 300 and minus 300 volts. Here's another question. All right, let's go ahead and solve this. So you need to add locations A and B, find the electric potential. So we need VA and VB. So let's go ahead and write this down. And this is going to be example 6, if I believe. 6. So we need to find VA and the voltage at B. Now you know your V equals KQ over R. So for part A, what you're going to have? You are going to have your K, 8.99, multiplied by this charge divided by 0.2, plus you got 1 coming in here, so it'll be your K minus multiplied by this negative charge divided by 0.4 and 0.2, which is 0.6. So let's go ahead. So that means your voltage at A is going to be your K, which is 8.99 times 10 to the 9th power. We said that Q, let me just write this down, 8 times 10 to the negative 9 on A. And on B is, or I'm just going to say A is the first one. The last one is minus 8 times 10 negative 9. So this will be 8 times 10 negative 9 divided by 0.2 plus the same dielectric constant, 8.99 times 10 to the 9th power, multiplied by minus 8 times 10 negative 9, divide that by, what we said, 0.6, 0.4, and 0.2, which is going to be your 0.6. Let me go ahead and do for part B. For part B, it'd be 8.99 times 10 negative, times 10 to the 9th power, your electric constant. Okay, so for this charge from B is 4. So it'll be 8 times 10 negative 9 divided by 0.4 meters plus 8.99 times 10 negative 9. And this is going to be 8 times negative 9. And this is going to be negative charge. Divide that by, how much is it? 0.4 from B. This will be 0.4. So what we get is, let's look. right, so I got 240 volts for this one, and I got 0 volts for that one. Correct. So let me just see what else we have. We talked about the equipotential surfaces, where now your book put your distance as S. So when you see D in mine, that's your S in your book for surface. So here's an example of equipotential surface. Go ahead and pause this video and work on it. Now, we also talked about your capacitance. Now, the magnitude of a charge on each plate of a capacitor directly proportional to the magnitude of the potential difference between the plate. Now, your charge is going to equal your capacitance multiplied by your voltage. Now, the unit of the capacitance is your coulomb per volt, which is your farad. I don't know if we wrote that down or not. So let me actually write this down. That means your capacitance is your charge per voltage, which is your coulomb per volt, which is your farads. Now, we also talked about dielectric constant, which is going to equal to E naught over E. And we define E naught as Q over epsilon naught A. So your capacitance equals your dielectric constant multiplied by epsilon naught A over D. And here's another example. Go ahead and pause this video, work on this example, see if you actually can solve it. It's pretty straightforward. And then the energy stored is equal to 1/2 CV squared. That means your energy density is going to equal to your energy over your volume, which is 1/2 dielectric constant multiplied per permittivity multiplied by your energy squared. And that should conclude chapter 19 for physics 102. If you have any questions, just email me at abunaem@uah.edu or you can call me or text me at 256-348-1480. Thank you.